What's up, good people? This is section 2.4, solving systems of equations graphically. It's called that because there's at least a couple of different ways of solving systems of equations, and today we're just going to focus on doing them graphically. Perhaps you've done this before in Algebra 1, but if you haven't, let's get right into it. So there are systems of equations are multiple equations that can be considered at the same time. So let's consider these two equations at the same time. The real question that we're looking for is what value of x and what value of y will solve both of them at the same time. One way to do that is just to graph them. So you can see there's a red equation and a blue equation, and I'm graphing the red, I'm graphing the blue. Now, if you want to find the one value of x and y that will solve both of them at the same time, that's going to be at their intersection right here. They both intersect at exactly one point, and so there's one solution. It's going to be -2, -4. That's where it is. You can actually check to make sure. It solves the, if you plug in -2 for x here, and -2 and -4 for y here, it solves the red equation. You can see -4 does in fact equal 3 times -2 plus 2. Check. Good. Then at the same time, it also solves the blue equation. You can check that as well. This is the x value, the y value goes there. -2 is the x value, -4 is the y value, and actually it does work. So we confirmed that it has one solution, and we checked it, and there it is. Here we can do the same thing. These were easy to graph equations, but it's also true for a bit harder to graph equations over here. Here's the red one, and here's the blue equation, and they're graphed. And there's one intersection point right there at -2, 1. It works both equations. So if you take x and if you let x equal -2 and let y equal 1, you can check to make sure that yes, in fact, it is a solution in both of them. You plug in -2 here for x, plug in +1 for y here, and it works. It's no longer y equals half times x plus 2. It's 1 is equal to 1/2 times -2 plus 2. And if you actually simplify the right-hand side, you can see that yes, 1 does equal 1. It's a true statement, so therefore we've checked and verified that it's the solution. You can do the same thing for the blue. Take a moment to think what you might what this red dot is covering up. We're checking the blue y equation. So the value of x goes here, -2, and -2 times -2 is +4 minus 3. You can figure out what's underneath that red dot. Things get a little hairy if the lines are parallel. You can see there's no intersections. They're railroad tracks, and so therefore, if there's no intersections, then there's no solutions. I'm graphing the line y equals -x, boom, here in red, and y equals -x plus 3. It's 3 units higher. All these points are 3 units blue. All these blue points are 3 units higher than their corresponding red points. So they're never going to intersect. So there's no solutions. Here's an even weirder case. What if we're graphing the same equation twice? Like y equals x plus 1, and if you subtract 1 from both sides, you get y minus 1 is equal to x. Well, if you were to graph them independently of each other, they'd be two lines basically coinciding, graphed directly on top of each other. There's actually an infinite number of intersections. Every point on this line is an intersection, and so therefore if there's infinite intersections, there's infinite solutions. And here's a few of them. 0, 1, it's right here. 1, 2 is right here. 2, 3 is right here. 3, 4 is right here. And all of these pairs satisfy all of these equations. You could plug this pair, 0, 1, into the red and blue, and you see that it satisfies both equations at the same time. So that's another possibility here. Let's go over some terminology. So a system of equations are multiple equations being solved or graphed or just considered at the same time. You can see the red and blue. In this case, there are 2 equations. It can get up to, in this class, it'll get up to 3 equations being solved or graphed or considered at the same time. But in practice, in reality, this is what the best computers in the world are working on, 50, 100 equations being considered all at the same time. And you can imagine graphing them in 100-dimensional space. It's really a complex computing issue, but it's a valuable one, and stock market computer programmers are considering 100 equations, 100 unknowns, all at the same time, trying to figure out maximizing things. So this is actually a real big deal and used a lot. Systems of equations. The solution to a system is a list of numbers, usually x comma y, like you see here, the solution, x comma y, that make all the equations true simultaneously at the same time. The big idea from today is that intersections on graphs are very related to solutions of the systems of equations. If you have an intersection, then you've got a solution. If you've got a solution, it's also an intersection. Boom. There are two major questions that we ask about systems of equations. And so this is like, here's the one question, here's the other question. And so it's a yes or no question. So therefore, there are four possibilities: a yes and a yes over here, a no and a no here, a no and a yes and a no. Let's talk about these questions. The first major question is, are there any intersections on the graph? Or if you're not talking about the graph, just the system generally, are there any solutions to the system? It's a yes or no question. Are there any intersections? Are there any solutions? And so yes would look like this. We've seen this. This is a graph of Rich and Julio on a race. They're on a road race. They're just running. It's like a 40-yard dash, and we're going to see who can get to the 40-yard line first. And this is time down here. So as you can see what happens here, Julio is faster, has a steeper slope, and Rich is slower but gets a 10-meter head start, or 10-yard head start. And eventually, right here, they're at the same place, and then Julio surpasses Rich and wins. There is, if you can say that yes, there is an intersection on the graph, and yes, there is a solution in the system, then it looks like this. It could also look like this, as we saw. If there's any, both of these are give a yes to the are there any intersections on the graph question. So if you answer yes, then the vocabulary word for today is called consistent. If it has any solutions, it's consistent. You can see this is consistent and this is consistent because it has greater than 0 solutions and intersections. No, then the opposite of consistent is inconsistent. You can see here there's 0 solutions. Boom. Here there are 0 solutions. Inconsistent. The other question that we want to ask is, it's the second question you ask. So once you establish if there are yes intersections or no intersections, you have to ask yourself, to find the solution set, was every line needed? So here, yes, we needed both of these lines in order to establish that there was one solution. But here, no, we didn't need both of these lines to establish the solution set. An alternate way to say this is, could you not have arrived at the same solution set with fewer lines or equations? Well, no, we need both of these to establish the solution set. Here it is. Here's the solution. Boom, there's one solution. And to get the solution set, we needed both of them. But to get the solution set here, no, we don't. There's duplicate lines. We don't need both lines to figure out where all the points are. There's an infinite number of solutions, and here they all are, and we could have just used one equation to do it. So because this is a no over here, this is dependent. Here, if you go to yes, then it is independent. Just to describe the graph over here, this is basically Rich and Julio starting at the same place and running at the same pace. Here, you can see they're running at the same pace, but Rich gets a 10-yard head start, and so therefore, if they're running at the same pace, they're never going to be at the same place at the same time. There are 0 solutions, and we said 0 solutions means inconsistent, and we needed both lines in order to establish the solution set. We needed both of these lines to see that yes, there are no solutions at all. Because we need both lines to arrive at the solution set, then we can say it's independent. It's a yes to here. Here, look at this. Check this out. What if we got 3 people? What if Mr. B joins the race? We got Rich and Julio running at the same pace and same time, but Mr. B also runs at the same pace and doesn't even start running until 1 second into the race. So there's still 0 solutions because at no point do all 3 of us exist at the same time. So zero solutions, that means no. That means it's inconsistent. There are no solutions. And you don't need all three of us, Rich, Julio, and Mr. B, to figure out that there were zero solutions. You only need two of them. Like if you just had Rich and Mr. B, then that would be enough to say that there are zero solutions. So that's a no also. It's dependent. Now might be a good time to talk about the audio check. Fun fact: I live very close to school in West Mount Airy. That's the neighborhood I live in. This is really tricky stuff, and I just want to go through the vocabulary. Consistent means a system that has one or more solution. Inconsistent is the opposite. It's not consistent. That is, it has no solutions. Independent is a system. It's yes over here. To find the solution set was every line needed. And here, if you get a yes, that means it's independent. It's a system where every equation is needed to find the solution set. Dependent, which is the opposite. It's not independent. It's that is, extra equations are in the system are not necessary for finding the solutions or the solution set. All right, let's take a quick break here to go over to our Inspire. Check it out. Grab those Inspire, pause the video, grab your Inspire, and when you've got your Inspire, you can unpause. And now they're grabbing their Inspire, turning it on, it's charged. Make sure you bring it to class tomorrow charged because we're going to need it. All right, so what I want to do, let's start at the beginning. All right, we're going to go to graph, B graph, and then as our first function, x times parentheses x minus 3, close parentheses, times parentheses x plus 3, close parentheses, enter. Whoa, this thing is all over the place. All right, next function, press tab and then 0.5 x plus 1, enter. Wow, we got a red equation and blue equation, red function, blue function being graphed. Menu. 6, analyze graph. We want to find intersections today. So for intersection. And so you're going to use I'm going to use the left or right arrows. You could also use the trackpad. I like using the left or right arrows. It's asking for the lower bounds. And now then you press enter and then go a bit more to the right, and then you can find the intersection. Once you give the lower bound and upper bound, there it is. Again, analyze graph for intersection. It wants the lower bound. You can see on the left-hand screen it's saying lower bound because you need to narrow its focus. Let's focus between there, press enter, and then go to the right a bit more. We know there's an intersection right there. Press enter. Boom. And there it gives you the next intersection. And let's do it one more time. It's getting really crowded on that screen. I want you to find the next intersection. Take care, and I'll see you in class.